good morning, good day to Spain Park Chemistry. This is another exciting installment of virtual online learning. We're going to continue our discussion today on solutions. This is going to be part 3, talking about solubility and interpreting graphs with solubility. But before we get there, let's just kind of take a quick review. We talked about solutions, and in talking about solutions, we realized that you can have a pure substance or you can have a mixture. Okay, pure substances are your elements and compounds. Elements on the periodic table, compounds where they chemically combine. But a mixture, they're just physically combined. We do not, chemically combine, so we can separate them with physical means. And we found that there were 3 types of crystals: a solution, a colloid, and a suspension. And so it's all based upon the size of the solute particle. So when you look at that, then you can just, really it's not easy to tell the difference between a suspension and colloid, but a solution is pretty obvious. And so if we go down here to this table, we can see the different characteristics of a solution, a colloid, and a suspension. The biggest thing here is we talked about the effect of gravity. It does not separate. In other words, a solute particle is not going to settle out. So when you have a solution, okay, I don't have any solutions left. When you have a solution, we can actually look here. If I look at this, this is I made the red precipitate on the last video. You can see the red sitting all on the bottom here. Okay, let me even blank this out. You can see the red sitting on the bottom, and then this is all the extra potassium chromate. This is the solution. So the yellow part didn't precipitate out because it's a tiny, tiny solute particle. Those are being kept agitated, kept stirred up by the continuous rapid motion of the water molecules colliding with that. It's called Brownian motion, after Robert Brown, and he lived in the early 1800s. He studied pollen grains on top of water and found that they just continually moved over and over, and he called it Brownian motion, but he didn't really know what was going on. Einstein explained it later, around 1905, that it was actually atoms bouncing around. So the solute particles don't separate. Okay, but the suspension particles are so big, gravity pulls those down, and that's the red precipitate. That's what we collected in the filter paper. Here, we collected the red precipitate in this filter paper. Okay, and so the difference between the 3 is strictly the size of the particle. Now, it's hard to tell a solution and a colloid apart because they can appear to be homogeneous. Sometimes you can't see the colloid particles. So we use the Tyndall effect to tell the difference. We shine a light through it, and if you can see the beam, that means the particles are larger. And so a difference between a solution and a colloid: solution, you can't see the beam; colloid, you can. I talked about seeing your car headlights on a rainy night. You can't see the beam because the rain has washed all the dust out. So this is, again, just another way to tell a solution and a colloid apart. Okay? Next time you go to the beach, beaches are going to be open pretty soon. If you can go to the beach and go at night, you shine your light up. If you can see the beam of light going up, it's pretty much been a pretty day, and that's the Tyndall effect because you can see your flashlight beam going up into the sky. If you shine it on a rainy night, right after it rains, you won't be able to see that beam, okay? Because there's no particles left in the air. All right, so those were our different types of mixtures. Then we went into the solution process, okay? And so we looked at the components of a solution, which were the solute and the solvent. I think most of y'all know that solute's what's being dissolved, the solvent's what you're dissolving it into, okay? And then we have different types of solutions, okay? Everything can mix in everything. Okay, one that we need to be aware of is alloys, physical mixtures, but we know 14 karat gold's an alloy. You guys can know pretty much that stuff, okay? Then we got into the solution process itself. What causes things to dissolve in the second video, okay? And we talked about electrolytes versus non-electrolytes. And so if I put salt into water, the light bulb came on. But if I put sugar into the water, the light bulb didn't come on, because we know electricity is the flow of charged particles. In a metal, the charged particles are electrons, but in a solution, they're ions. So there are 2 ways in which solutes dissolve. They either dissolve as an electrolyte or as a non-electrolyte. Electrolytes, by definition, dissolve as ions. Okay, so we talked a lot about how they dissolve as ions, and there are three types of electrolytes are always going to be ionic compounds, which we call salts, a strong acid, and a strong base. Those are your strong electrolytes. A weak acid, weak base, they'll still be electrolytes, but they're not going to have as many ions, so we're going to call it a weak electrolyte. All right? Now, so these, we went through all these examples of how ions dissolve, and a base, remember, has the hydroxide ion, acid has the H plus ion, but those are the things that dissolve as ions in solution compared to covalent substances like sugar that actually don't break apart, they dissolve as neutral molecules. And so that's real important. So electrolytes dissolve as ions, covalent compounds dissolve as neutral molecules. Ions in solution will conduct electricity, compounds, neutral molecules will not. One other tidbit on that, you may have heard the word electrolyte in Gatorade. Gatorade replaces the electrolytes your body so desperately needs. Well, what's an electrolyte? I don't know, but my body needs it. Well, the electrolyte is actually just going to be, salt. Okay? That's all it is. But salt has such a bad reputation that we can't say, hey, go drink Gatorade, it's got a lot of salt in it. Well, no, because salt's got a bad nutritional reputation. But the reality is our body needs the salt. When we sweat out salt, so we have to replace it. So they were ingenious in marketing it. Hey, it replaces the electrolytes your body needs. Well, it replaces the salt that you sweated out. But they can't really market it that way because people will freak out with salt. Okay, so then we talked about what are the factors that affect solubility. What makes one thing soluble, another thing not? So that's when I did the demonstration with the styrofoam cup and the acetone. Well, here's the remainder of the styrofoam cup. It dissolved completely in the acetone, and over the last 3 days, the acetone all evaporated out and left the styrofoam cup back just kind of as this flat piece of styrofoam right here. But the styrofoam didn't melt and change, it just dissolved, and then the acetone evaporated, and we got the styrofoam back, just not quite in the same shape. But styrofoam is nonpolar, acetone was nonpolar, so they dissolved. When we put cyclohexane and the water together, okay, the iodine dissolves completely in the cyclohexane, goes purple. You can see it's a little bit of an amber kind of color, a little brown color. So there's a little bit of iodine dissolved, but not much because water's so polar and iodine's nonpolar. These two liquids don't separate, they're immiscible because one is polar and one is nonpolar. So when you have two liquids that don't dissolve, they're immiscible. Two liquids that do dissolve are miscible. Then we talked about the strength of this, and that's what we're going to really focus on today. Okay? And then this is just real quick, how do we make things dissolve faster? Well, we know you make things dissolve faster. 3 things we can control. 1 we can't. 3 things you control. Number 1, how big the particle is. If you want to make something dissolve, you crush it. Okay? If crushing it, then you stir it, and worst case scenario, you heat it up. Okay? Now this is the one you can't control. You can't control how concentrated the solution is. I mean, I guess you could, but the reality is if you're trying to dissolve the sugar in your iced tea, you're going to crush it up, you're going to stir it, and you're going to really make the best sweet tea by dissolving it in hot water and then putting your ice in and making it cold water. Okay? And then lastly, we talked about how much actually dissolves, and so that's your solubility. Okay? And we talked about we can either be unsaturated, saturated, supersaturated, having less than the maximum amount, and in these rare cases have more than the maximum amount. And so you need to watch this video, that video, to kind of see a supersaturated. But the reality is we just need to think about saturated and unsaturated. Unsaturated means anything up to the maximum amount. Then once you get the maximum amount, the rest just sits on the bottom. Okay, and we're going to look at that today as well. So the way you tell the difference on these solutions is you can add a crystal. If it dissolves, it's unsaturated. If it just sinks to the bottom, it was supersaturated. But if more and more comes out, it was saturated. If more and more comes out, it was supersaturated. Okay? So just dissolves, it's saturated. One sinks to the bottom, it's I'm messing this up completely. If it dissolves, it was unsaturated. If it sinks to the bottom, it's saturated. If more comes out, then it was supersaturated. I got it right that time. All right. So, how does pressure? Pressure doesn't affect solids and liquids. Pressure only affects gases. And so we talked about that. The clicker can't keep up with me. So if I open up a nice 2-liter bottle of Diet Mountain Dew, okay, then we have all kinds of pressure of the CO2 above here, about 5 atmospheres. So all that CO2, that means we have a whole bunch of CO2 here. You take this off, loosen it up, it goes down to 1 atmosphere. Immediately you see bubbles coming up because the solubility was decreased by 5 times. It's a direct proportion. And then I related this to the thing called the bends in scuba diving, and I recommend that you read that. I'm actually going to post a little article on the bends and what happens in scuba diving on that, so you can just kind of read about that. But that's Henry's law. Pressure doesn't have any effect on solids and liquids. Okay? Now temperature, okay? We're going to talk about what effects temperature has today on solubility curves, okay? So let's get going with this. Get my computer back up and running. All right, so when we look at solubility curves, okay, I'm just trying to get up to where we're all together on the same thing, okay? If I look at this curve right here, this shows the solubility, the y-axis. This is grams of salt. In other words, grams of NaNO3, grams of calcium chloride, grams of lead nitrate, grams of salt per 100 grams of water. So we're comparing apples to apples. So I have all these different beakers, 100 grams of water in each one. That'd be 100 milliliters. Okay? How much? What's the maximum amount of each one of these? What does it take to make a saturated solution? Okay, at any given temperature down here. Hopefully you can see that temperature. Okay? You can see that most things have a positive slope. Most things increase in solubility as you increase the temperature. There are a few. Here's one right here, the cerium sulfate. It just decreases, and so its solubility actually goes down. Okay? If we look at gases, gases all kind of go down as well. The solubility of a gas decreases with an increase in temperature. Now you can see the increase is different for every substance. That's going to be based upon its heat of solution. We'll talk about it in a bit. Salt, very little change in temperature, change in solubility with change in temperature. Okay? And so when we look then, okay, so how do we read this chart? What is the solubility for CaCl2 at 25? So when we say what's the solubility, that means what's the maximum amount of calcium chloride that I can put into 100 grams of water at 25 degrees. So I go and I find 25 degrees. I find calcium chloride. So I'm going to go up, 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 up. Calcium chloride's right here. I'm going to hang a left right there. And it's going to be somewhere around 85. It might be just a hair above. It might be 86, 87. Okay, now the good news is with sig figs, the last digit's uncertain. So 85, 86, 87 are all going to be correct answers. What, did I read that wrong? 25. Calcium chloride. Calcium chloride. Ooh, right here. Okay, so you might want to scratch through that and put 85 right here. So 25 going up, okay? And we, 25 going up. I can actually live with 90. I changed my mind, okay? I kind of slid to the left as I was going up, okay? And so right here 90, but again, there's a lot of leeway on those numbers because of the only one sig fig on all this. So you don't have to be exact on that, you just have to be approximate. Okay? What about 20 grams of KClO3 at 100 grams, per 100 grams, okay? So at 55 degrees. So if I go, what am I looking at? KClO3. At 55 degrees right here, I come up, and this KClO3, a saturated solution, is 20 grams. So at 20 grams at 55, it's going to be saturated. Okay, I already pushed the button by accident. Okay, but if I go to 80, KClO3 is right here. Okay, so it's going to be just less at 80 degrees. It's just going to be less than this 40. So it's going to be again anywhere in that 30. Well, it's I'm not even reading the question right. Okay, I want to classify it as saturated, unsaturated because at 80 degrees, maximum you can have is somewhere around 38. But if you only have 20, that means it's unsaturated. 38 is the maximum you can have. So if you only have 20, that means you have room for 18 grams more per 100 grams. Okay, let's see. I've been obviously staying in the house way too long. The bread is beginning to mold. It'll go crazy. Kind of get back in the flow of things here, but just bear with me. We're making progress. Now, if we look at this last one, how much more solute can be dissolved if you have 30 grams of KCl dissolved at 50 degrees? So we go to 50 degrees, we go to KCl. Well, the maximum you can dissolve of KCl at 50 is somewhere right around here, around 42. Okay, 42, 43. If we have 30 grams dissolved already, the maximum you can have is 42. That means you can have about 12 to 13 grams more. Okay? So, it all depends. Now, you could have very much said 42. And again, this is the last digit is uncertain. So if you said 42 and it had 12, your answer is 100% correct. Okay, so you don't stress over the one or the two, but you should be able to guesstimate that it was below the line here at what temperature were we at? We were at 50 degrees. Okay, we're definitely kind of somewhere right up in here above this line, not quite halfway. So we should be able to estimate those values. Okay, so you should be able to read these graphs. Pretty straightforward. Now here's a question for you. This is per 100 grams, but it's a ratio. So if I know that at 10 degrees, 80 grams of NaNO3 will dissolve in a 100 grams. So if I have 200 grams of water, well, then I can put 160 grams in. If I only have 50 grams of water, well, then I'm only going to be able to put 40 grams in. So it's going to be always going to be a ratio. This tells me how many grams per 100 grams, but we can just, then determine, multiply by, how many grams do we have, use that as kind of really set up a proportion, and we can get that value, okay? So we should be able to do that as well and figure that out. So if we have 300 grams of water, we're going to multiply this 80 grams by 3, and it'd be 240 grams of NaNO3, okay? So even though it's per 100 grams, we can use this and figure out how much for any amount of water. Just set up a proportion, okay? So here's a comprehension check for you. So you can go ahead and pause the video and do this and read the graph, and then we'll come back later on and go over all these comprehension checks with you. So go ahead and pause your video and do this. There's one on this page, and there's another one on the second slide there. All right, so that's interpreting graphs. So hopefully, that's pretty straightforward. I think that you guys can do that and read those graphs. That's good practice for your ACT. They have all kinds of questions like that on there. Now, the enthalpy, and again, whenever you see this word enthalpy, it's like a foreign language to you. Translate that into the word heat, okay? Heat, the heat of solution, okay? That is the amount of heat that is absorbed or released. In other words, does it get cold, does it get hot? Endothermic, it gets cold. Exothermic, it gets hot. Endothermic, it absorbs energy from the water to dissolve. It requires that energy. Or exothermic, when it dissolves, it releases energy. Okay? So we get the overall heat of solution. Now this is not in your slides, in the notes, but the reality is what happens over here is that the heat of solution actually is 3 different things. When you dissolve salt into water, okay, here's a whole bunch of water molecules. Okay, they're all stuck together with their hydrogen bonds and their IMFs. Here's your salt held together by the ionic bonds. Okay, in order to make these 2 things come together, the first thing we have to do is break the ionic compounds apart, the solute to solute. We have to overcome that lattice energy, the ionic bond holding these 2 things together. So it's got to pull it apart. The second thing that has to happen is the water molecules have to move apart, break apart from one another in order to be able to make room for the ionic compound. And then lastly, the ionic compounds and the water have to combine together, and you can, I don't know if you can see it or not, but you can see them attaching here, and so they have the solute to solvent attachment. So there are three processes that are occurring kind of simultaneously. The attachment of the solute to the solvent, that attachment of the water coming in, and we saw the video of that, when these come in here and attack, okay, if I can make them stick here, okay, they come in and attack. Now they're going to, this attachment, this attraction between the solute and the solvent is what causes these first two things to separate. But this takes energy, okay? That requires energy. This requires energy, a positive heat of solution. This one releases energy. So all three things, whenever you break bonds, breaking bonds always requires energy. Okay? There's always going to be a positive heat of solution. This is bonds forming. This is forming bonds. Okay? That's always going to be a negative, an exothermic, a release of energy. So the overall heat of solution, it depends upon how strong are the bonds. Really, we call this is known as your lattice energy. Lattice energy. If it's an ionic compound, if it's an ionic solute, if it's a covalent solute, it's going to be the IMFs that you're going to have to overcome. Steve, can't remember how to write on a board. Okay? This is if it's covalent. So, in other words, you have to break the bonds that are holding the particles together. A sugar molecule, it's hydrogen bonds and dipole-dipole attractions holding them together that have to be broken apart. And salt and any ionic compound, it's ionic bonds, which we refer to as the lattice energy. You have to break these bonds. The water molecules have to move apart, it's positive, and then the energy coming here, we call this the energy of hydration. This is the energy released when the bond forms between the water and the solute particle. So, math-wise, you have two positive terms, one negative term. Whichever is greater, the sum of these two, if it's greater than this one, that means the overall value is going to be positive. If the sum of these two is less than this one's greater, the sign is going to be negative. So some of our substances have a negative heat of solution, some have a positive heat of solution. It all depends upon the strength of the IMFs or the lattice energy holding this together compared to the strength of this attraction here. And this attraction between the water and the ion, we call this, and we talked about that before, the ion to dipole attraction right there. Ion to dipole attraction. So the key on this is that if it's a positive heat of solution, you increase the temperature, you increase solubility. So that's easy. Positive means increase in solubility. If it's a negative heat of solution, that means an increase in temperature is a decrease in, let me try this again. I gotta learn how to talk again. I haven't talked to anybody in 3 or 4 days, so I'm stumbling. If you have a negative heat of solution, that means that as the temperature increases, the solubility decreases, okay? And so as we go through then and look, okay, in an endothermic reaction, you have to add energy to make it dissolve. You have to put this much energy in. That energy, you don't really add it in. This energy comes from the surrounding energy of the water. So since energy goes into breaking the bonds, the temperature of the water goes down. The solution gets cold. Okay? In an exothermic reaction, heat is produced. Okay? So that means in this one, the energy of hydration is greater. So you put some energy in to break them apart, but more energy is released overall, so that this release to the water, so the water ends up getting hot. Okay? So energy is released. So this all determines on the sign of your thing. So if it's positive, the solution gets cold when you dissolve it, and that's how disposable ice packs work. You mix the two things together and they dissolve, and as a result, then you end up having, it gets super, super cold. Okay? It has a very positive heat of solution. Okay? Hand warmers, some hand warmers use a chemical reaction that then as it dissolves, it releases energy. And so it all depends upon what you have and what you're mixing together. So if I look at these two graphs, notice all of these with a positive slope, they're going to have a positive heat of solution. Now, KNO3 is going to have a very positive heat of solution. So when I dissolve this, it's going to get really cold. Salt, on the other hand, when I dissolve this, there's not going to be hardly any temperature change at all. Consequently, as I increase the temperature, solubility greatly increases here, but with salt, it doesn't increase hardly at all. Notice the cerium sulfate actually decreases. This would have a negative heat of solution. All gases have a negative heat of solution. Their solubility decreases as you increase temperature. So as you, if you leave a soda out in the heat, it goes flat because the CO2 that's dissolved in it becomes less soluble. There are more fish kills in the summertime than there are in the wintertime because fish have to struggle more for oxygen in the water at the higher temperatures than in the cold temperatures. Okay? So any little disturbance to their environment in the summertime can have disastrous results. So the steeper the slope, the bigger the value of the heat of solution, temperature will have a greater effect on solubility. That's a super important point right there. Okay? So notice delta H of solution of salt is 3.9, where delta H KNO3 is 34.9. Much bigger difference. So as it has temperature, has a much greater effect. Okay? And if it has a negative heat of solution, that means the solubility goes down. You need to be able to understand this graph. So if this still isn't making sense to you, kind of go over it in your book, maybe look up in your book. If not, email your teacher, and you guys can kind of have a discussion on that because this is really important right in here. Understanding the relationship between your heat of solution, the steepness of the slope, the positive or negative slope, and how that affects the solubility. Okay? So that's really important. All right. So there you can do, you stop, you do your comprehension check, number 3. So that's the end of part 3. So I encourage you kind of go back and forth on this. Really, really, really focus on interpreting those graphs, doing those comprehension checks, looking at that. And again, if you have any questions, email your teachers, and I can even try to address some of those in our next session. So again, hope you're having a great day. Hopefully you're adjusting to this new style of learning. And again, if you ever have any issues with getting online or internet or anything and getting the assignments done, please email your teachers. Thank you, and again, if you're enjoying these videos, please feel free to like this video and subscribe to my channel.